Good morning, students. Today our topic is carbon ion 2. సో రీసెంట్గా మనం కార్బన్ అయాన్స్ గురించి చెప్పుకున్నాం. దాంట్లో కన్సిక్వెన్స్గా కొన్ని రియాక్షన్స్ ఉన్నాయి. సో జనరల్గా మనకు వీ హ్యావ్ ద టూ టైప్స్ ఆఫ్ కార్బన్ అయాన్స్ ఉన్నాయి. సో అందులో ఒకటి వచ్చేసి మిథిలిన్ యాక్టివ్ మిథిలిన్ కాంపౌండ్స్ గురించి చదువుకోవడం. ఇంకోటి కార్బన్ అయాన్స్, హౌ టు ప్రిపేర్ ద కార్బన్ అయాన్స్ విత్ ద హెల్ప్ ఆఫ్ మెటల్స్. సో నౌ-a-days we are using so many carbon ions. So generally in this topic, regarding this topic, we have the instantly prepare the carbon ions with the help of active methylene compounds. So what are the active methylene compounds? The methylene group, both sides have the electron withdrawing groups. Like here we take the Z is the electron withdrawing groups. In the middle of the methylene group act as a active methylene. So it is readily loose of proton from this methylene carbon to form the carbon ion. So that is the important one of these compounds. So this is about the active methylene compounds to readily form the carbon ion. So this form the carbon ion is more stable, so that's why this active methylene easily form the carbon ion. So generally electron withdrawing groups increase the stability of the carbon ions. So electron donating groups decrease the stability of the carbon ions. So that's the reason of these compounds. We are using this electron withdrawing groups of like cyanates, nitrate, and carbonyl and acetone. Like these groups are we are using for this esters and the acids we are using as the electron withdrawing group according to plus IE minus IE groups. So generally the minus IE groups act as the electron withdrawing groups and plus IE groups are the electron donating groups. These groups are act as the electron withdrawing groups. It is increase the stability of the carbon ions. So that's why we are using this electron withdrawing groups. So here we have the simple example of this. It is easily loss of proton from the active methylene compound. One of the active methylene compound, this is the carbonyl involving the loss of proton to form the carbon ion. So always the adjacent carbon of carbonyl group as a alpha carbon, the alpha carbon lose the proton from here to form the carbon ion. This carbon ion is stable because of these carbon ions involving in tautomerism further to form the enolate to form a stable carbon. So in this enolate, the negative charge, the carbon negative charge transfer into the oxygen. Always highly electronegative oxygen atom negative charge is a more stable, so that's why it is a stable compound. When compared to carbon ion, this enolate is more stable, so that's why it is easily involving in this process to form the enolate. So this is the stabilization factor of the carbon ion. Because of these electron withdrawing groups to increase the stability of the carbon ions. Okay, one of the example of ethyl ester, ester. So generally the ethyl ester one of the to readily form the carbon ion. In this case, so the carbon ion here, the ethyl acetate, we have the middle of the methylene group. I have the two electron withdrawing group, one of the ester group, another one carbonyl groups. So this ethyl acetate also act as a good carbon ion formation. So that's why we are using this ethyl acetate. Yesterday we are studying about this ethyl acetate compound. So the general name of IUPAC name of this compound is 3-oxo-ethyl butanoate. So that is the IUPAC name of this compound. So this is the one of the example of active methylene compound. Okay, so let's we start with simple preparations from this active methylene compound. Like we are preparing from so many compounds from here. So first we start with the simple examples of like preparation of carbonyl compounds and preparation of carboxylic acid. So generally this ethyl acetate involving in two types of hydrolysis process. One is the acidic hydrolysis process, another one the ketonic hydrolysis process. In both cases we are using the same reagent, but the different is the concentration. For example, in case of this both hydrolysis process, the acidic hydrolysis. So generally we are using concentration HCl and concentration KOH in this hydrolysis process. In ketonic hydrolysis we are using dilute HCl and dilute KOH hydrolysis. In both cases we are getting the same reagents we are using, but the different is the products are different. In acidic hydrolysis we are getting the acidic product. In ketonic hydrolysis we are getting the ketone is the product. Let's see what is happening in the ethyl acetate involving in the hydrolysis process, what is happening. So we start with the simple example of acidic hydrolysis reaction. This is the we are using a whatever the catalyst we are using. The catalyst or concentration HCl and concentration KOH. So in this concentration HCl and concentration KOH, the hydrolysis take place in two places. One is the break from the carbon between the carbonyl between the carbon, the middle of the methylene group, and this is the ester hydrolysis. It take place here. So what is happening in hydrolysis where addition of H plus and OH minus group. So generally H plus have the positive charge and the OH minus have the negative charge. So in addition to that, the carbon between the carbon here, the carbon have the positive charge and this carbon, methylene carbon have the negative charge. So that's why the H plus addition here and the OH minus addition. Here the carbon between the oxygen, we can break the bond between the carbon and oxygen to form the acetic acid. In this acidic hydrolysis, we are getting the acid is the product. So that's why it is called as acidic hydrolysis. In ketonic hydrolysis, we are using dilute HCl and dilute KOH. This dilute HCl and KOH are very less hydrolysis process involving in this process. To here, the only ester group is will be involving in hydrolysis. Finally, we are getting this carboxylic acid group, carboxylic. After that, this carboxylic acid, after that we are conducting it to lose the carbon dioxide from the air. Finally, we are getting the acetone product. In acidic hydrolysis, finally we are getting the acid product, and this ketonic hydrolysis, we are getting the ketone is the product. So that's why this is called as a ketonic hydrolysis process. Okay. Example of preparation of ketones from ethyl acetate. So this is very simple reaction. First of all, the ethyl acetate involving in this reaction, the sodium ethoxide. In presence of sodium ethoxide, this reaction is start with the sodium ethoxide process. The sodium ethoxide generally we can break into the sodium plus and ethoxide ion. So this sodium ion further reaction with the ethyl acetate. What is happening? The ethyl acetate reaction with this sodium ethoxide. So the proton lose from the methylene active methylene compound, then the sodium is substituted by the proton in the first steps. So this is happening. So then second step, the this compound reaction with alkyl halide to form the um, substituted uh, alkyl substituted ethyl acetate. Alkyl substituted ethyl acetate. So then after we will hydrolysis in this ketonic hydrolysis. Finally we are getting this product. After that we are use eating. So finally we are getting this carbonyl compound ketone is formed. So when you prepare 2-butanone preparation, we are using what are the R group. In place of R, we are using the methyl iodide. Methyl iodide is the product. So this is the simple to prepare the ketones from this. For example, if you prepare the pentanone 2-pentanone, so we are using ethyl group. Ethyl halide as the group is the we are using. So this is the process to prepare so many compounds from this ethyl acetate to ketones. So these are the reactions generally. Next one, preparation of monocarboxylic acids from ethyl acetate. So this is also very simple reaction. First of all, the ethyl acetate reaction with the small sodium ethoxide, small amount of sodium ethoxide. This small amount of sodium ethoxide to reaction with sodium ethyl acetate. So the proton is substituted by the sodium. Here the proton is substituted by the sodium. After that the RX. So Rx mean any one of the alkyl halide. So here the R is the positive charge and the X is the negative charge. Here also the between the carbon and sodium, the carbon have the positive charge, sodium negative charge. We can break the bond between the carbon and sodium. So the carbon reaction with the allied group to form NaX. NaX byproduct and NaX byproduct. This is the R is substituted by the active methylene compound. R is substituted by the active methylene carbon. So that means we are preparing so many monocarboxylic acid from here. So this R is, for example, we can substitute different types of R. We can prepare different types of carbonyl compounds from uh, formic acid to decanoic acid. We have the number of carbons increasing, so we are getting so different type of carbon. So this is happening. So it is after that with this compound we can hydrolysis in acidic hydrolysis. So finally we are getting acetic acid plus this is the R substituted carbon compound. So here they break the two steps process to bond here. So finally we are getting this product. For example, if you prepare butanoic acid, propanoic acid, in place of R in butanoic acid we take the ethyl group. In place of uh, propanoic acid we are substituted methyl group. So that is the mean we take ethyl halide to prepare the butanoic acid from here and methyl groups so substituted to prepare the propanoic acid. So this way we are preparing so many compounds of carboxylic acid. So let's we see what is happening, how many carbonyl comp series. So we can see these are the homologation series of carboxylic acid. Methanoic acid we have only one carbon, and propanoic acid and propanoic acid. Butanoic acid we have 4 carbons chain. Pentanoic acid 5 carbon chain, and heptanoic hexanoic acid 6 carbon chain, and this one heptanoic acid 7 carbons, and the octanoic acid 8 carbons, and this one nanoic acid 9th carbons, and decanoic acid 10th carbons. So these are the homologation prepares from acetic acid. That means we are using ethyl acetate compound to prepare from um, from acetic acid. That means ethanoic acid to decanoic acid. We can increasing the alkyl group chains to prepare the so many compounds from this ethyl acetate compound. So that is the important one from ethyl acetate to prepare so many carbon chains increasing from these compounds to prepare the so many compounds like from ethanoic acid to decanoic acid of monocarboxylic acid. So the major difference in this ethanoic acid, ethyl acetate involving in the acidic hydrolysis. That means we are using concentration HCl, concentration KOH to prepare these compounds from ethyl acetate. The first of all, this we are preparing the R substituted ethyl acetate compounds. After that R we need the preparation. What are the product we need? We are preparing. For example, we are preparing ethanoic acid. There is no R groups are present. Only we are preparing simply. If you prepare propanoic acid, we need one more carbon. So that's why we are adding the methyl group. If you prepare butanoic acid, we may need 2 more carbons. So ethanoic acid preparations. So we can prepare so many carboxylic acid, monocarboxylic acids from preparation of butanoic acid. We need two uh, carbons chain substituted 2 carbon chain. In propanoic acid we need only 1 carbon chain substituted. That means methyl group substituted on the ethyl acetate. In butanoic acid we are substituting ethyl group. So that is the difference. This reactions to continue the prepare the homologation series of carboxylic acids. So next we have the so many preparation of dicarboxylic acid also. So in dicarboxylic acid, so we are preparing 2 moles of ethyl acetate. The substituted sodium substituted 2 moles of ethyl acetate. After that we can link with the CH2 iodine methylene groups. Iodine methylene diiodide methylene. Now here the number N is increasing number of the carbon chain. We take the number of carbon chain to prepare here. For example, what are the homologation series of this dicarboxylic acid? From the oxalic acid to we have the climatic acid, like for example, if you take, these are the common and IUPAC name of dioic acids, like ethanol-dioic acid, that is the IUPAC name of oxalic acid, and the common name is oxalic acid. So in two carboxylic acid groups are present in these carboxylic acid groups. So one is the ethanol-dioic acid and malonic propanol-dioic acid. So the three carbons are present in malonic acid, common name, and the four carbons, so that is succinic acid and butanol-dioic acid, and five carbons and dicarboxylic acid we called glutaric acid, common name, and the IUPAC name is pentanol-dioic acid, and six carbons dioic acid, we carboxylic acid we called adipic acid. So the IUPAC name of this compound is hexanodioic acid, and the seven number of carbons dicarboxylic acid we called as a phenolic acid, it is heptanodioic acid. So in subbaric acid we have the 8 number of carbons present in this carboxylic acid, and this is octanodioic acid, azoleic acid, so nonanodioic acid. So that means 9 number of carbons are present in this carboxylic acid. Sebacic acid, so that is 10th number of carbons are present in dicarboxylic acid, that is sebanic acid and decanodioic acid. So using this ethyl acetate compound to prepare the dicarboxylic acid from the oxalic acid to sebacic acid. So these are the so many dicarboxylic acid we prepare. How to prepare this? So how to prepare this dicarboxylic acids? First we start with the 2 moles of ethyl acetate reaction with sodium ethoxide to prepare the sodium substituted ethyl acetate come 2 moles of. After that, these 2 moles to reaction with CH2 diiodide methylene compounds. This methylene is injected in between the sandwich type reaction. This is the two between the two ethyl acetate compounds. After that, this CH2n substituted here. So after that, we are conducting acidic hydrolysis process. Furtherly, we are getting this compound. So this is the very important intermediate where n is equal to integers. How many n substituted? We are preparing different type of carboxylic acid from here. So this is the way to we are preparing the so many dicarboxylic acids from ethyl acetate to prepare. Okay. The second one active methylene compound is the malonic ester. So this is also very important one. The malonic ester came from malonic acid. So the malonic ester to prepare the malonic acid, esterification to prepare the malonic ester. So the malonic acid, generally we know about the propanodioic acid is the malonic acid. So the 3 carbon chain is present. So this propanodioic acid involving in esterification reaction to prepare the malonic ester. So this is the malonic ester. In the middle of this methylene carbon act as a active methylene compound. So that means it is easily involving in the deprotonization process to form the carbanion. This carbanion form of this carbanion is more stable because of this carbanion involving in the tautomerism process to prepare the more stable carbanion formation. Okay. Let's we see what is happening of this methyl malonic ester. So this is the simple form of the malonic ester. The middle of the between the two ester group, middle in we have the CH2 groups. So here the two ester groups are acting as electron withdrawing groups. So that's why this middle methylene group act as a good carbanion formation group. So this is the ET means CH2 CH3 group, ethyl group. Okay. So let me start with the preparation of malonic ester from acetic acid. సో ఈ రియాక్షన్ నేర్చుకుందాం ఈరోజుకి. ఇది ఫైనల్ అయిన తర్వాత నెక్స్ట్ ఇంకొక రియాక్షన్ గురించి మనం తెలుసుకుందాం. ఫస్ట్ ఆఫ్ ఆల్ వి స్టార్ట్ విత్ ది సింపుల్ రియాక్షన్ మెలోనిక్ ఎస్టర్ ప్రిపరేషన్. అది ఎలాగో చూద్దాం. ఫ్రమ్ ఎస్టిక్ యాసిడ్, సో వి స్టార్ట్ విత్ ద ఎస్టిక్ యాసిడ్. సో దిస్ ఈస్ వెరీ వెల్ known famous named reaction, HVZ reaction. This reaction conducted by three famous scientists, Zelensky. The name of this reaction is HVZ reaction shortcut. This reaction is alpha halogenation at carboxylic acid position, alpha halogenation. So that means the carboxylic acid adjacent carbon, so that is alpha carbon involving in this reaction to form the alpha chlorination. So this chlorination take place in presence of red phosphorus. So what are the reagents we are using? Chlorine in presence of red phosphorus to prepare the chloroacetic acid. So to prepare the chloroacetic acid, after that this chloroacetic acid reaction with the potassium cyanide. What are the charges on the potassium cyanide? The potassium positive charge and cyanide negative charge. So the cyanide substituted by the chlorine, the remaining product KCl is byproduct, as a byproduct. So this cyanide, between the carbon and nitrogen we have the triple bond in hydrolysis process involving in acidic medium hydrolysis process to form the carboxylic acid group. So that means the carbon between the nitrogen, the carbon has a positive charge, and nitrogen have the negative charge. Because of their electronegativity differences, the carbon and nitrogen, the nitrogen have the 3 electronegativity and falling scale, and carbon has 2.5. Finally this is the carboxylic acid. Finally we are getting this product what is the product we are getting? Malonic acid is the product. After that this malonic acid to reaction with ethyl alcohol in presence of acidic medium, this reaction we call as a esterification reaction. Esterification reaction to form the malonic ester reaction. So to form a malonic ester reaction, so this is very simple reaction, the malonic ester to form here. సో ఓకే, ఇది నేర్చుకున్నాం. మళ్ళీ మనం రేపు మళ్ళీ ఇంకొక టాపిక్ తోటి వద్దాము. ఓకే, లెట్స్ వి సీ వాట్ ఈస్ హ్యాపెనింగ్ టు